I guess this is a bring your own markers kind of whiteboard. All right, let's get started here. So I'm pleased to welcome you to the Wireless Communications Lab. I appreciate those of you that took the time to get up early, find your way over here to this unusual classroom. So this is a course that is all about wireless communications, and what's particularly innovative about this course is that it has a laboratory component with it. And so today's lecture, I'm just going to tell you a bit about the class. So we'll go through the syllabus, and then we'll spend some time talking about wireless communications, establishing terminology, and then I'll wrap up with what to expect for the duration of the course here. So with that, let's get started. There's syllabus in back of the room, syllabi. Are there any extras back there? You pass one up to the front here. I realize I gave all of mine out here. All right, thank you. Here, that's good. All right. Well, so I guess before we get started here, so just a quick introduction. So I'm Robert Heath. I'm one of the faculty here in the ECE department. I'm director of the Wireless Networking Communications Group. This is our logo here. This is a center within the Cockrell School of Engineering, and so it has 20 faculty, about 130 graduate students associated with it. I've been at UT now for, I guess this is my 13th year. Seems like it's not been that long, but it has. And then I've been working in wireless ever since I really started on my master's degree in the 90s. I won't tell you exactly when, but it was a while ago. I guess I'm approaching the point where hopefully most of you were born after I started my before I started my graduate studies, I think. And so one of the interesting things here, so up here, I'm also a registered professional engineer. This, for all practical purposes, means nothing. I'm a professor, so I'm not really doing any real engineering. But it turns out that if you do any work on legal cases, the jury is much more impressed if you're a professional engineer than if you're a doctor of philosophy, right? Because if you're a jury, you don't have high school education, which sounds more impressive. Oh, they're a professional engineer, of course. The other thing to note here is this is my amateur radio call sign. I admit I don't do much, but we'll talk about this at some point in the course here. So there are opportunities to actually do wireless communication, on your own, in your spare time, and I'll tell you a little bit about how that works here. And then finally, this is my webpage address here. If you've checked my webpage lately, either it looked strange, it didn't load, or it looked different than you looked at it previously. So I'm in the process of upgrading it right now. Once my web page is stable, I will start posting more material there, but right now everything is posted on Blackboard. Okay, so that's some administrative stuff here. This is the outline for today. I will tell you that for the most part, I will lecture on the document camera by writing. So I'm just not a big believer in PowerPoint, but for the first lecture, it's convenient because I have a lot of material to cover. So I will do this here. So first of all, syllabus here. I've handed out the syllabus. This is my favorite color for the syllabus, which is yellow. Hopefully you can read it well here. We won't read through it in detail here, but some of the finer points that you may wish to observe here. One, we have a teaching assistant, Yingjae Lee. He has another conflicting class right now. He's a graduate student in the WNCG. He took this course last year, so he's familiar with all the challenges that you're going to face, and so he's going to be an excellent TA. His office hours are listed on the syllabus here. Right now they're Monday 1 to 3 p.m. and Thursday 2:45 to 4:45, and we may have an additional office hour Wednesday. The key deliverables in this class will be pre-labs, which are due Tuesdays, homeworks, which are due Thursdays. And so his office hours coincide with, roughly those two deadlines there. And then he's hopefully going to come by at the end of class to introduce himself here. All his office hours will be held in ENS 113. That's on the first floor. That's where the wireless lab is, so you'll be going over there. My office hours will be in my office, which is the unlabeled black door on the 4th floor. At some other point, I'll explain to you why it's black and why it's not labeled. There's a story there. Okay, so other things here. Prerequisites. So this is a cross-listed class. It is cross-listed for both undergraduates and graduate students. The undergraduate students have a firmly enforced prerequisite of one of these 3 classes here. Actually, it should be 445S now. I suppose none of you have taken 345S, but it's either 445S or 351M or 360K. And I see some of the students from my 351M class, so I know that you have that prerequisite. But if you're an undergraduate, you have to have taken one of these courses here to enroll, and it'll make sense because we'll use either the signal processing background, primarily from 351M, but you get enough of it in 345S that it works there too. And then if you don't have the signal processing background, but you've seen digital comm in 360K, it'll actually be okay. You just have to brush up more on signal processing. The reading materials. I've gotten a few questions about where is the book. So I have posted everything on Blackboard early this morning. On Blackboard, there's multiple sections of the class, and I asked them to combine the sections. They might not have been combined yet. So if you don't see anything, you should see it by tomorrow. I apologize for that. I forgot I had to combine the sections into one Blackboard course interface. You'll see the course reader there. It's about 250 pages. It's a textbook that I've written. The benefit of me writing the book and posting it there is that you don't have to pay for it. So it's free. So that's good. I suppose I should at this point ask you for a tip for giving you a free book. I'm pretty sure the university will not let me do that here. Or I could do that if I disclosed it in my financial conflict of interest plan. But at this point, no. So I am actually working on submitting that for publication. So this actually will probably be the last year that it's free. I mean, I'm hoping I can get it published, and there's one more chapter I need to add. Along those lines, there's possibility that I will make updates to the book. Last year I did a pretty thorough revision, and so I don't foresee making many changes. The only thing I might do is I might integrate some of the problems from the homeworks from last year into the book. So I encourage you not to print it out this week. If you're going to print it next week, because I'll go through and check that everything is up to date later this week here. And if you can, just don't print it. I mean, save paper and all of that here. All the homework problems that I've ever given in this class, and some in 351M, and some in some of the other classes I've taught, are all in that book as problems or examples. So, and exam problems too. I try to mark the problems that are exam problems. So, I typically won't provide, previous homeworks or previous exams, because you have examples of everything there. And I encourage you to use that when you're studying for the exams, because the reality is I've taught the class so many times I cannot think of really any new problems. So pretty much I'll think of a new problem. I've had this happen many times. I have a new idea for a problem, and then I write it up. I'm like, oh, this is great. And then I look in the reader and I'm like, damn, I had it already in there. Just many times it happens. So use that to help study here. Okay, so other sundry things. This is a tech area in communications networking and signal processing. If you're a graduate student, this counts as a ComNets course. So if you're not in ComNets, then this can be an out-of-area course for you. Final point. This year, the class is being videotaped. That's why we're in this room here. My plan is actually to make the video recordings just publicly available on my website. I don't know. It seems like to be like the cool thing to do now. And I think it's a good thing to do. Now, I know this is dangerous because I'm telling you I'm video recording it. The class is at 9 a.m. And so I'm imagining some of you are thinking, well, I'm going to sleep in and catch the course in the video later. I suppose that's possible. The video may be put up a few days or a week later. But I do hope that you make the effort to come to class here. It's also kind of painful to lecture to an empty room, which I've done before when I videotaped classes. There's a few days that I will be out on business travel, and those days I will pre-record the video so that you can watch it at home, or I suppose we could roll the video in here if you really wanted to. Okay, so that's it, the syllabus here. Let me check if there's anything else here I should note. I will explain a bit more about this later here, some of the details about grading. One thing I do want to mention is that I take the plagiarism and cheating seriously, so please be mindful of that and read the lengthy academic dishonesty policy here in the back. Okay, so that's just basic review of syllabus. I'll come back and talk more about the course at the end. Any procedural questions about syllabus or some other non-technical question? All right, I suppose not here. That's good. Let's continue here. Okay, so now is like the motivation for the class. The idea is, of course, you get excited about wireless, you want to stay in the class. This is kind of obvious at this point. Wireless is everywhere. I mean, we are being penetrated right now by tons of different wireless communication signals. Most everyone here has at least a smartphone, if not also a computer and a tablet. And each of those devices has multiple different wireless transmission technologies built into it here. Some of the most common ones that we're going to talk about, and one of the reasons I like to introduce this here is I want to introduce terminology and use some of these as examples. And so even though we won't talk much about standards in the beginning part of the course, I will still try to draw from these different example areas to explain how what's in the course connects to reality. The four kind of major places where wireless is playing a big role right now: cellular networks, local area networks, personal area networks, and then there's a whole bunch of new applications coming that I'll tell you about here. First, I'll talk about cellular. Cellular is close to my heart. I mean, most of my research, probably 80% of it, tends to be in cellular. I mean, I didn't really start out that way. It just kind of happened that way. My background is in multiple antenna communication, and you'll notice most of the time I put multiple antennas on everything here. This is actually a phone I created, clip art that I created when I did my PhD defense. So I've been getting a lot of reuse out of that. So think about it. When you create graphics, you could get 15 years of use out of it. Amazing. So cellular is a big deal here, and it's really been perhaps one of the wireless technologies that really has changed the world and changed how we connect with each other. So the cellular concept itself, so this is like along the lines of terminology here. Again, another gratuitous figure for my defense presentation here. The cellular concept is essentially as follows here. There are base stations, which are these triangular-looking towers here. Most of the time now, the antennas are mounted on buildings, and they don't look quite so ugly like this. So there's base stations that are geographically distributed, and so the distance between these might be hundreds of feet, or it might be thousands of feet. You could say half kilometer or tens of kilometers in rural areas. The couple of key things about cellular. One is that so these base stations are distributed over a large area with the idea that you can cover many different users. And then so you can cover those users at the same time, we reuse some of the frequencies. And this is a rather dated picture now because most systems do better than this. But here I have a tessellation of hexagonal cells. And these 7 cells here split up a common set of frequencies. And this frequency is reused here. It's reused here. This frequency is reused here, reused here. It's reused far away because that frequency interferes with transmissions that are happening over here. So you want it to be somehow distant, and there's other ways of reducing interference that we'll talk a little bit about in this class, and we'll talk more about in my advanced graduate class next semester. So the key things with cellular systems, so first of all, the notion of a cell. It's the area that's covered by a base station. And a lot of times we think about cells as being hexagons, but in reality they're irregularly shaped. You might also think of them as circles here. The frequencies are reused. And then finally, there's handoff, so that when you go from one area to the other, your call is maintained throughout its duration here. And of course it's not perfect. You get dropped every so often. But that's kind of the key things behind cellular here. Base station subscribers. The mobile phones we call typically mobile station or user equipment. So in like standards, they usually call it UE, user equipment, because it could be something else other than a phone. It could be a tablet or something else here. So that's the concept. Now, to give you a little bit of historical perspective, I'm going to talk about 1G through 5G. So cellular systems, each successive generation has a name. The first one we call first generation. Of course, when it started, it didn't have a name because it was the first one. But now we call it 1G. And cellular, it was really conceived in the 60s, and the first deployment happened 79, 80, 81. And these were analog phones. One of the lectures I'll bring in, I actually have one of the early phones from about 85, these brick phones. It's really cool looking. I'll bring that in one day. So these were purely for talking on the phone, believe it or not, like just for talking, right? Nothing else, talking to other people. And they were built around analog technology, FM modulation in particular. So the communication between the user equipment and the base station was all using a variation of FM, just like in FM radio. Different details. There was very little support for data, in particular like fax. I mean, you had to sort of squeeze the fax into this voice FM modulator here. Fax did not work well. There was really no text messaging, let alone like actual other sorts of data there. There's also little security in that system. It turned out that with a radio, you could tune in and hear people's conversations. Now, typically, because the frequency talking to the base station was different than the frequency talking to the user, you couldn't hear both sides easily, but you could hear one side. And there was a famous scandal in Virginia, which is where I grew up, where one of the congressmen was discussing, actually maybe it was the governor, was discussing something inappropriate on the cell phone, and it got recorded and then became a big scandal. And that's harder to do nowadays. These phones, they were expensive because they use analog technology, analog circuit components. You can't take advantage of Moore's law. And some of the examples of these standards are AMPS is the one that we used in the US. There's NTT, NMT 450. NTT, I think, was the Japanese standard. NMT is Nordic. That's like Finland, Sweden, Norway, and et cetera here. Now, I realized as I was putting this together today that probably none of you have ever used an analog cell phone, so I was kind of sad. But that's good news. I only actually used it for like a couple years, so I actually don't feel too much like a dinosaur here. So there were a lot of issues with 1G, but the biggest one was that the system was such that it was hard to support a lot of users. And if you want to make a lot of money, it's typically better to have a lot of users that pay a little bit than a few users that pay a lot, because usually you can charge those many users a little bit more and make a lot of money. So I understand. So second generation systems were conceived in the 80s and deployed in the 90s. So typically with all these cellular systems, there's about a 10-year cycle between when people start thinking about it and when it gets deployed. And so here, this started rolling out in 89, 90. Biggest innovation here is two things. One is it used digital communication instead of analog, and it used digital voice. And so what I mean by digital voice was that the voice was actually compressed, so it was like sampled, converted to a bit stream, advanced vocoding algorithms were applied to compress it down, and those bits were sent over the digital communication link. And that was a huge revelation. One of the benefits of that, so you get all the advantages of digital communication, many of which we'll talk about next week, but you could take advantage of Moore's law, and it can make it more secure, it can be more robust. But also, when you use this digital voice compression signal processing, you can compress the voice a lot, like a lot more than you could do with analog. And so you could get more users in the same spectrum, means more customers, more people that can pay a $100 bill each month. Good news if you're deploying cellular systems. One of the quirks about cellular is this whole notion of roaming and compatibility. So in the US, we had basically a monopoly, and so AT&T had 1G deployed like all over the US. The coverage was phenomenal. I mean, rural areas, mountains, everywhere, because they would just deploy one base station that would cover like 20-mile radius. It's like 400 square miles. So you had really awesome coverage. And then in Europe, many countries had their own standard because they all want to develop their own thing. And so then there was, like you'd be like in the UK, you'd go to France, and your phone wouldn't work anymore. Then you'd hop over into Belgium, it wouldn't work. Just examples, I don't remember which standard was used where here. And given how small the European countries are relative to Texas, naturally, you'd be roaming like all the time, and cellular phone, not as useful here. So in Europe, they got together, developed the GSM standard that, and they did it in a way that was kind of like a collective effort. And they divided up the standard among different countries, essentially. And so different countries played different roles in development of different pieces of it. As a result, they came up with a very efficient standard that was used all over Europe, and not in the US until much later. In the US, we developed, we had this startup that many of you have heard of now called Qualcomm that created this standard IS-95 based on CDMA technology. They came around. There was another standard, IS-136. This was a digital standard that enhanced the amps setup, used kind of a similar channel configuration. That's like completely dead now. And then later on, the US, we got GSM, but we still have a mix of standards. So we ended up with IS-95 and GSM, and then now we have other variations of that here. So most of you have a phone that supports most likely GSM or IS-95, depending on which carrier you have. Now, as they've been evolving here, so in the late 90s and then deployed in the 2000s was third generation, which we call 3G. 3G you're probably familiar with because it's become a marketing buzzword, and most of you have the phone that has 3G. Some of the biggest differentiators here, I mean, one was it was designed to support data much better than the 2G systems, where data was a bit of an afterthought. It had higher capacity. What this means is that you could support more users in the same spectrum. In particular, you could support more voice users in the same spectrum. And you could get that in different ways, compressing the speech better, using better digital communication techniques, better coding, and so on. And it exploited a suite of those techniques. It used code division multiple access as an access strategy. It supports things like video telephony, has not caught on in the US yet, but has in other places in the world. So some examples of this are wideband CDMA, and then CDMA 2000. So depending on, like if you were, AT&T, you'd be using one of these variations, and Verizon or T-Mobile, Verizon, you were somewhere down here, depending on the year. So this was an evolution of the GSM family, and this was an evolution of the IS-95 family. So we ended up with kind of two different standards, both serving the same purpose. And so that's like 3G. Now, 4G. So 4G is also becoming a big term in marketing here. And in 4G now, devices are probably being deployed. Maybe some of you have one. After the development of 3G when it rolled out about 2000, they started doing essentially updates to the standard. So instead of doing like another completely new standard 10 years later, they decided they would try to do more frequent updates. And so they started doing yearly revisions, and they started giving them names. R7, this was 2007, 8, 9, 10, 11, and so on here. And sometimes the changes were more incremental, and sometimes they were more substantial. And at some point, the changes became quite different. They adopted a different physical layer that uses multiple antennas and OFDM modulation. Uses more bandwidth, different kind of an access technique. They changed the network configuration. We won't talk much about how the base stations are networked, but there was a big change that happened that made base stations networking much more inexpensive and cheaper. Supports higher data rates, and essentially, higher data rates and higher data rates. That's the main thing here. Actually, the voice support was not emphasized really in 4G. So a lot of times if you have a 4G compatible phone, when you make a phone call, it goes back to 3G for the phone call, and then it would use the 4G for the data. And that's a problem for a lot of reasons, because it means carriers have to have spectrum for voice and spectrum for data, and that's not an efficient way to use things. So anyway, so 4G is here, and so generally you'll see this term. So 3GPP is third generation partnership program. And you'll see the term long-term evolution advanced, or LTE advanced. That's really what I consider 4G. And that would be release 10 and greater. So yeah, that's 4G here. And believe it or not, we are now on the verge of defining 5G. So there's a lot of discussions right now about fifth generation cellular systems. And what will they be? What will they look like? What will they support? What will be the new feature? So 2G, the new feature was digital. 3G, it was it's really data and CDMA. And 4G is multiple antennas and OFDM. So 5G, what will it be? Will it be more of all of those or something else? Well, it's it's under development here, and we probably have 30 or 40 PhD students in the wireless group here looking at these issues. In my opinion, and we'll look at this video in 5 years and see if I was right or not. But I mean, these are the two front-running technologies that would change in a substantial way 5G and make it really different from 4G. One is called massive MIMO. So MIMO stands for multiple input, multiple output. It's this multiple antenna technology. Massive MIMO, you could have hundreds of antennas at the base station instead of 4 or 8 right now. Natural question, where do you put them? That's a whole other question entirely. Millimeter wave spectrum, where you use 28 gigahertz or 38 or 77 and use very large bandwidths. Both of these are really interesting technologies. You know, I'm actively researching them in my group here, and they could end up defining this 5G setup here. You know, we won't talk so much about a lot of these kinds of technologies in this class. If you're a graduate student, though, I encourage you to do a project that maybe focuses on something in this area here. That'd be useful. It might not just be physical layer type technologies, signal processing. It could be other features that make 5G interesting, like device to device. It can more seamlessly support communication directly from, you know, like me to you all. Like if we want to talk or exchange a photo, why should it go through the base station and come back if we're sitting 10 feet away? Doesn't make any sense. But that's how it would happen right now. So device to device could be interesting. Machine to machine, there's a lot of interest in just putting wireless in basically everything. I mean, it's been in like, you know, soda machines for 20 plus years. But you can put it in almost every commercial machine. You can put it in your home appliances. You know, they can communicate back, report service. They can also collect data. You know, and there's a lot of people that are interested in mining said data. Certain security agencies, among others, but you know, there's a lot of opportunities to generate data, and companies use data for marketing, and they sell the data, and you know, other people use the data. And then vehicle to vehicle. Right now, wireless in cars is kind of primitive. I mean, we can use our cell phones, sort of. We're not supposed to, but maybe we do. But the cars don't really talk to each other in any intelligent way. There's some vehicular radar, but there are protocols where cars can talk to each other. One car can warn another car, hey, there's traffic up ahead, apply your brakes now, collision is imminent. All of these things could be supported and could be enabled by 5G, and they're not widely supported right now. So these are some places that cellular is going. Okay, so that's a little bit about cellular. I'm going to move into local area networks. Any questions on cellular, though? I mean, we should stop for a second here. Ideally, I get some questions at some point, because then I might as well just lecture to myself, and you know, I could just video ahead of time. Yes, question. The first question of the whole semester. Excellent.
The different generations that you're talking about, is it normally like trying to define the protocols that support these communication features, or what's like the difference between the generations?
Yeah, the difference, I mean, that's a good question. And so my background is like signal processing and communication. And so I tend to think about them from the perspective of what happened in the physical layer of signal processing. But each of these generations had innovations in essentially how, so the physical layer is all about this class, how we communicate between the transmitter and receiver. But they also had innovations in how the base stations are networked together. What are the components of that network? How do they communicate efficiently? So there are also innovations made there, too. I mean, some of the differences are, I don't know as much about the backbone networks there, but like in 4G, for example, they changed around the communication protocols between all of the, there's a ton of networking equipment that's used to support cellular. So we see the base station, but there's tons of other equipment in there. Like when you make a call, they've got to figure out, you know, where are you? How do we bill you? Are you roaming? There's separate boxes for all of the stuff here, and they're all networked together previously with like proprietary type protocols, protocols that were standardized but not like internet protocols. So now there's been interest in, you know, making it all communicate with like IP. And so I guess the short answer is yes, there are differences at all the different layers, but I'm just giving you my biased perspective. Okay, good. The other questions here? I'll try to answer a shorter fashion here. Yes?
How do they generate the cells, and how don't they interfere with each other, like the cells created by different base stations?
So generate the cell meaning like how do I get the coverage
how do they
area or?
emerge? Yeah, how do we have them?
Well, okay. I mean, there's sort of an engineering answer, and I mean, basically. So first of all, a cell itself is created by having a base station there. So essentially, there's a set of antennas. Those antennas are connected to power amplifiers and DSP and networking. So to deploy a cellular system, you need to deploy antennas in various places. Now, this is a bit tricky because initially, when cellular systems were deployed, what you wanted to do was cover as many people as possible because building that tower is expensive. But the problem is, like, if you cover all of Austin with one tower, you can only support like 20 or 30 people at a time. Not enough people. So then that's where they decided, okay, and the key thing behind cellular is frequency reuse. So instead of deploying one tower in this area, let's deploy 7. And then maybe if you've already got 7, you would look at this and say, I got a lot of traffic over here, so I'm going to deploy 7 more here and make this, and that's called cell splitting. So you take this cell and then you deploy 6 more base stations, and then it becomes another bunch of little hexagons there. There is a whole, whole industry around like modeling propagation. There's industry around predicting coverage. Selling base stations, leasing base station sites. And nowadays, where you deploy a base station is not so much, I need a base station here. It's more like, can I get a base station here? Because you basically need base stations everywhere, and you can't put them many places. And so, building owners will make money by leasing their base stations. I don't know if maybe I'm going on the total tangent here. Does that sort of answer your question?
Yeah, I got it.
Yeah.
I thought one base station generates multiple cells.
Okay, so you have to be a little bit careful with the terminology. I maybe have not been clear, but there are different notions of cell. So some people, each base station here, nowadays the base stations have sectored antennas. And so there's an antenna that looks this way, another antenna that looks this way, another antenna that looks this way. And so some people call those 3 things a cell. I call the whole thing a cell. But yeah, so nowadays, you can use directional antennas to create effectively, you could call them like multiple cells. And that you can use to get more capacity too. And that's also used widely now. But pretty much only in that configuration of taking one base station and converting it into 3 sectors. That's the most common. Okay. All right, other question?
Yeah, as we are heading from one generation to another, what is the trend of use of frequency bands? Like, are we going towards higher frequencies? Are we going towards higher bandwidth or like ultra wideband or something like that?
Yeah.
What's the trend?
Yeah. So there's basically 2 questions there. The one question is the carrier frequency that we're going to be using. The other is the bandwidth that is supported. So the carrier frequencies, we started off in 1G with 850, 900 megahertz, and then went to 1.8 to 1.9 gigahertz and 2G. 3G, a little bit more spectrum was opened up. Some countries at 2.1. 4G, there was some other extra spectrum that came available, but not really uniformly everywhere. There was also spectrum that opened up at 700 megahertz when people started releasing the TV bands. So actually, it went low there. And low frequencies are nice because you get better coverage. But at this point, the microwave bands are really saturated. And so if for 5G we want more spectrum, it really is not going to come at 2 gigahertz and below. It's probably going to be 5 gigahertz below if it's microwave. Or it's going to be 20 or 30 gigahertz. That would be the millimeter wave solution. So, so the general trend is that more spectrum is allocated when we go to a new technology, but it's kind of opportunistic as to where we can fit that spectrum in, because all spectrum is essentially used. And so when you, like in the TV bands, we had to move TV broadcasters off of those bands, and that cost a huge amount of money to get those people to leave.
So are frequency agile devices seen in near future, like in mobile technology?
Yeah, frequency agile devices that could leverage what's called like white space. I mean, I think they will be there, but it fixes it fixes the problem of that, you don't have a lot of spectrum, so you get a little bit more spectrum. But it's not like you get 100 times more spectrum. It's like you have access to another 50% more or something. So it's not, it's a valuable solution, but it's not a defining feature of like 4 or 5G. They will probably support it, I mean, the essential thing is that if there's spectrum around, cellular providers want to use it, especially, though, if it's licensed spectrum. The problem with a lot of those spectrum agile solutions is that you end up with spectrum that is shared in some fashion, and then you can't necessarily guarantee the quality. And then if you're not going to guarantee the quality, you might as well be, using Wi-Fi or some other solution there. Cellular providers are offering a service that you pay money for, and you expect reasonable quality. And the cool thing the service providers have done is that they just keep ratcheting down the quality so that we keep paying, and then we put up with dropped calls and no service, and it's just brilliant marketing, right? Oh yeah, 100 megabits per second data rate, and you get that like at 5 a.m. if you're standing under the base station with your phone pointed at the tower here. But it's marketing. They don't tell you how often you get it. Just that in theory you could get it. Okay, I guess I'll continue with wireless LAN here. So I don't have as much to say about wireless LAN, but essentially the concept is very similar to cellular systems, except that so we have, instead of base stations, we call them access points. One of the things you'll notice is that the wireless industry loves to create new terms for things. And so they could have called the base station, they call it access point. I mean, I don't know why. A lot of times it has to do with intellectual property and so on. But anyways, there's a box here that communicates potentially with multiple users. Nowadays, a wireless LAN, originally it was a wireless extension of a LAN, a local area network. And originally it was computers connected together. In a company, you'd have a database over here, and you'd access that database, and you'd do some work. Nowadays, wireless LAN really means wireless access to the internet. I mean, that's what we all think of. Primarily when we think wireless LAN here. And so typically this access point is connected via Ethernet back to a switch, and that switch is then connected to a wide area network and then back to the internet. The access points, they serve multiple users, so you can have, in this case in 3G, like in wireless LAN, they call them clients instead of user equipment or mobile station. They call them clients. Access points serve multiple clients. One of the main differences with cellular is we use unlicensed frequency bands. In cellular systems, all the bands that are used by cellular providers are licensed, meaning that they have to pay a government money to communicate in those bands. And by pay government money, I mean a lot of money, like maybe hundreds of millions or $1 billion to use 10 megahertz of spectrum. It's very, very expensive, that licensed spectrum. Unlicensed spectrum, everyone can use as long as they have a protocol and a waveform that matches the requirements of that band. So you can't like do whatever you want there. You have to create a waveform that meets the expectations of other potential devices and behaves in a sort of a nice way. So it's unlicensed, so it typically uses, actually I have that on the next slide here, but either 2.4 gigahertz, 5 gigahertz, or 60 gigahertz. Another main difference between cellular is that there's either little or no coordination between access points. Actually, the de facto is no coordination at all. But some enterprises, they have some coordination between them. So what that means is that when you're walking from one room to the other, you may lose your connection. Now like here at UT, you probably won't, because we have this restricted wireless LAN, and there's all this mechanism set up to support that. But generally speaking, you're at Starbucks, you step outside, and you walk down the street, you're hosed. And even if there is an access point there, the really annoying things, you have to like log in and check all these buttons, and even if you could get on there, you still have to do all this other stupid stuff again. So it's a pain. You don't have to do that in cellular, right? So that's a nice thing here. So that's like two of the main differences here. There's other differences as well. I mean, they're from a from a networking perspective, they're much simpler, because pretty much this connects with other networking infrastructure. So there's not all this other infrastructure to support roaming and handoff and billing. None of that is there. The physical layer strategies are much more compact. We will talk about one of these standards in the class here. The standards for wireless LAN, if you print it out, it's about that thick, like the phone book size. And if you print out the standards for cellular, it would be maybe the whole wall here of books. Not just the physical layer, but because they have everything standardized in the whole system. And it's a hugely complicated system. So it's an easier standard to deal with. It's also cheaper. The parts are cheaper. So there are different, around the world, different wireless LAN strategies, but the one that has become the de facto standard is built around IEEE 802.11. So IEEE, digression here, hopefully you know this, Institute of Electrical and Electronics Engineers. I suppose that most of you are an electrical engineer or an electronics engineer, and hopefully you're a member of the IEEE. I encourage everyone to become at least a student member. One, it's like super cheap. You get discounted access to all these conferences, especially if you're a grad student. You would want that, and you can join societies as well. ComSoc, Communication Society, SPSoc is Signal Processing Society, ITSoc is Information Theory, and so you can join the IEEE and become a student member and join these other societies very low cost, and you get the free magazines in each of those societies, and you get access to, you also get access to various sundry things on IEEE Explorer, but we have that for free at the university, so it's not a huge benefit. So IEEE is, in theory, it's okay. In reality, it's a nonprofit institute. Doesn't mean that they don't make and spend money. It just means that they don't have a profit. And one of the things that they do is they coordinate the development of standards. And they have different standards. The one that is called IEEE 802 is the group that develops local area network and metropolitan area network standards. And so what they specify is what's called the physical layer. That's kind of the action we're going to see in this course. The MAC layer, medium access control, and link layer. From a networking perspective, these are layers 1 and 2. That's what IEEE standards typically specify. Cellular standards, by the way, specify like layers 1 through 5 or 6. And so they're going to tell us essentially, how devices should communicate and how they should access the channel. So 802.11 is the wireless LAN working group. And so within this working group, there's going to be various subgroups. And so if you're in a working group, you can become a member. If you have to attend a certain number and there's a certain procedure to follow, and then at some point you could vote, and then you could provide input and votes and actually shape the way the standard works. Since its original development, most of us don't have any device that supports 802.11 anymore because that specific standard is now superseded by many more advanced ones. And these are some of the different subgroups. So what they've done is they've attached a letter to the end of 802.11. So it's 802.11b and G and N. These are the most common ones. There's also 11a. And then they ran out of letters. And so now they're doubling up. So we have AC, AD, and A, blah, blah, blah. And then as 26 letters later, we'll end up with B and C and D. And, it'll just keep continuing. So the next 100 years. Some of the features of 802.11. So each of these they're not all actually started or finished, I should say, in exactly this order, but this is roughly how it happened here. And these are some of the features here. I mean, the original 802.11 standard supported a 0.5 megabit per second. That seems terrible now. And it used one of 2 physical layers, a frequency hop spread spectrum or a direct sequence spread spectrum. And one of the interesting things about that standard was if you bought a device that supported frequency hop spread spectrum and you had an access point that supported this, they didn't work together. They didn't talk to each other. That's kind of silly. But the reason is the way these standards work is you have to have there's certain voting rules. So like you need like a majority vote, and then at some point you need like a 2/3 majority. And so what happens is compromise is often the case. And so in this case, there were 2 different groups. They could not agree. So they agreed to disagree and said, okay, since neither of us was going to be chosen as the standard, let's both be chosen, and the market will decide. So the consumers get screwed because they don't necessarily realize this. And then one or the other becomes popular. And in this case, it turned out the direct sequence spread spectrum one became popular. And then there was 11B, which came out with 11 megabits per second, and then A, 54 megabits per second. This is 2.4 gigahertz band. This went to 5 gigahertz band. 11G is more or less like 11A, but is in 2.4 gigahertz. A couple small differences. 11N supports MIMO, so up to 4 transmit, 4 receive antennas, 100 to 200 megabits per second, maybe 400 depending on the configuration. If there's bandwidth aggregation and so on, you could almost get up to, let's see, 400. Yeah, 400 is probably the practical limit there. AC is the one that is now out in devices. You may have a device that has AC. That's very high throughput, so it's 2.4 and 5 gigahertz. It aggregates more bandwidth. It uses more antennas, supports multiple antenna techniques. So that's like rolling out right now. The other one, which is really cool, is 11AD, and this is using the 60 gigahertz unlicensed band. There's 7 gigahertz of spectrum there. And 11AD is going to come out in probably this next year. And so you're going to start having devices that support AD, AC, N, G, B, and A, all in everything you buy. It's all going to be packaged together. So anyways, that's pretty exciting. That's 11AC and 11AD basically done. So now there's discussion about what's next. And I don't know what the letter is, but if it's been assigned yet, but it will be there soon. That's wireless LAN. Any wireless LAN questions? Yeah. Well, I guess the question, what would we do with Google Fiber, or?
What one of those categories of Google Fiber?
Well, Google Fiber is a wired solution. Fiber's, fiber's glass, but I call it a wire. So, yeah. So I'm not talking about fiber stuff. Where Google Fiber fits in, one is that if your access point supports 200, 400, a gigabit per second, but your home DSL supports 20 megabits per second, how fast do you access the internet? Well, you access it at 20 megabits per second. So where this fits in is that Google Fiber would give us the data rate to exploit what's available already in the standard here, right? So now we're just limited by the rates that get into our apartments and homes. And with Google Fiber, that will go up by 2 orders of magnitude. And then, then we can debate about the societal implications of that. Are we going to watch, 4K Netflix, or what's the implication? There's a whole bunch of other cool things too. We can have potentially a lot more coordination among access points. We can do a lot more cloud computing, and there's a lot of other benefits potentially too. Yeah, so I'm excited about that. I'm hoping they're going to come in my neighborhood and put it in. I'm also hoping they're not going to dig up my yard and put it in. Yeah.
So when you have two adjacent access points, which use the same standard.
Yeah.
So what happens? When there's overlapping region where
Yeah.
both are.
Yeah. That's like the situation. Most urban areas, you turn on your laptop and there's like 15 access points, and there's in principle only a few channels. So the way the medium access control protocol, so that's what the medium access control protocol does, is it facilitates access to the medium, which is the wireless space. And so the protocol, essentially they behave in a nice way. If there's a user, like once you're associated with an access point, depending on which flavor of the protocol you implement, you might send out your packet, and then that access point that is destined for listens, tries to decode it, and then the other one hears that you're sending a packet and that the medium is busy, so it doesn't send anything. So there's mechanisms for collision avoidance, sensing if the medium is used. And
Slows down the.
yeah, it slows it down a lot more, and then not by half. Half is kind of like best case. So it'll, like if you have 2 access points working, maybe you'll get best case half of the capacity, kind of worst case maybe a fourth or an eighth, or some catastrophic failure. Catastrophic failure won't happen, but it'll be not favorable. Yeah, data rates are crappy. Yeah, but the cool thing though is it does work though. It doesn't just collapse. Now, if you put a bunch of people on the access point, that's when it tends to collapse. Like the typical hotel, convention center, conference room, kind of problem that a bunch of people put their put their laptops on and just breaks the access point. And that's just, there's so many people that you just can't get enough of the time on that access point to send any data. But it doesn't break. So, that's a good question. Now, there is some interest in coordinating. So if those 2 access points, they're connected to a wire. Why can't this one talk to that one and say, hey, let's be friends and work together. So there's work on that now, and you can do a lot better. Oh, any other questions? Yes.
On that millimeter wave you're talking about the cellular
Yeah.
use earlier, is there any sort of coordination right now between the 80 protocol and I guess kind of that research into 5G to maybe do that same thing, work together to maybe handle backhaul or over your home network, or at least keep them from interfering with each other?
Yeah, there is interest in using 11AD for backhaul for cellular, first of all. So, but the cellular system, if it's based on millimeter wave, will not use 60 gigahertz because that is on licensed band. So cellular system will use a licensed band, just a different band. And so, they won't talk to each other because they're on different frequencies. But it doesn't mean that we can't use what we learned in 11AD to design those cellular systems. And this is, I have 2-3 students in my group working on this right now. So this is it's a big question. The idea of using millimeter wave for cellular is becoming very hot right now, but it's really only been pursued by a few research groups so far. There's a couple companies, and so it's a really, really new area. You won't see this in most classes. It's a good thing. That's the benefit of being at a research university. You get to see research. Okay, I'm looking at my slides here. I have 20-some slides left, but anyways. Personal area networks. Let's skip over this here. This is Bluetooth. I think is the main one. There's a 60 gigahertz version for HDMI cable replacement that has not gotten popular. What we're seeing now is that personal area networking functions are sort of being taken over by wireless LAN, and so Bluetooth and it was designed to be very low power, much lower power than wireless LAN. But many of the other functions, for example, communicating with your printer. Well, most printers now support wireless, they have Wi-Fi. They don't support Bluetooth anymore. HDMI, you could do with 11AD instead of doing it with 15.3C. So, the boundary is blurring, and I foresee that we could end up seeing the personal area networking space kind of diminish and be replaced by local area network. It's really interesting I'm being videoed here because I'm now thinking okay, whatever I say is going to be online and going to be here for the next 5 years, so I have to be very careful now. Not to say too many obnoxious things to offend other people and companies. Okay, wireless. I told you about 3 application areas of wireless that you're already familiar with. Hopefully you've learned some of the terminology there. There's tons of other places where wireless is important. We talked a little bit about car area networks. That doesn't have to be done with cellular. There's another Wi-Fi protocol that allows vehicle-to-vehicle communication. It's 802.11. What is it? V? No, it's not V because that would make too much sense. 802.11. I think it's P actually. And then there's other opportunities there. Body area networks. This is really cool where you've got sensors on your body talking to each other. You may have a pedometer that records how many steps that you take. You may have a heart rate monitor. These may be talking to your phone, and you may be taking that information and using it for some other purpose, like figuring out how healthy you are, or how you can burn more calories in the day, or our good friends at a certain agency could use that information to figure out if you're stressed and planning something devious, I suppose. That's actually a good idea. We should probably patent that. That's a good proposal, actually. All right. That's why I need paper to write these ideas down. Mobile ad hoc networks. These are networks where there's really no base station, but users set up a network over the wireless in an ad hoc fashion. This is used extensively in the military, Army, Navy, Air Force. You need it in the battlefield because you don't see soldiers walking around putting up a big base station. Now that said, mobile ad hoc networks, for a lot of reasons, are very inefficient, and so often they do exactly that. They go in and put up a base station. But there's a lot of research to be done there. Power line communication, there's wired applications, of course, over the power line. There's also wireless. Particular area networks, different from, so this car area network could be network inside the car, networking the components of your car. This could be networking to the cars. Underwater, we have a research center affiliated with UT Applied Research Labs. They do a lot of sonar and underwater communication. They do experiments out at Lake Travis, what's left of it, and so they do tons of cool stuff there. So basically, there's other applications as well. There's applications in oil and gas, which I'm really excited about now. Big money there. Big money. Yes, big money. All right. Okay, so that's kind of a little bit of background about wireless. Now, let me, in the time remaining, tell you a little bit about like the class. You're all here for the class, not to be entertained. Tell you about the philosophy that I've taken in assembling this here. So what you see on the left here, this is the OSI Network Model. If you take any communications class, you'll see these layers in this order, defined in this way here. Physical layer, data link layer, network layer, transport session, presentation, application layer. For the most part, we're going to focus on the physical layer, and we may talk a little bit about MAC and medium access control protocols, and maybe occasionally I'll mention some things that have to do with logical link control. But for the most part, physical layer. Physical layer is where all the action is in terms of the signal processing algorithms, at least in my opinion. Now, the physical layer can be broken up into two pieces. Now, depending on who you are, you associate one or the other of these with the term physical layer. But the reality is that physical layer includes the algorithms that generate the waveforms and process them. It also includes the antennas, the circuits, the hardware. All of that is physical layer. Now, if you're coming from circuits area, you're thinking, yeah, the circuits is the physical layer. And if you're coming from communications and signal processing, you're thinking, oh, that's the physical layer. So to be fair, they both are. For the most part, in standards, though, when they talk physical layer, they actually mean this. Because often these are implementation specific, and they're left up to the person building a standard, right? So the standard might tell you that you have to support this kind of modulation, but it doesn't tell you have to use this kind of a CMOS process and this kind of a transistor and this kind of an amplifier. It doesn't tell you that at all. So, and for the most part, we're going to focus on signal processing aspects of communication. And these are important, definitely important, but it's only so much we can do in the class, and so we're not going to do that. Now, this is a typical digital communication system. You will see this figure again next Wednesday, and then progressively through the course, we're going to dive in to certain blocks here. Typical system operates as follows here. There's source. This is kind of information theory parlay here. This is the box that generates the bits we want to send. There's source coding. This is compression. So this could be sampled speech. This could be a speech vocoder. Channel coding, we add redundancy to help resolve if there's errors. So this is all about the bits. Then here, modulation is the magical box that takes our bit sequence and creates a waveform, analog waveform. Digital communication, we always send analog waveform. There's no, we're not actually sending 0, 1, minus 1. We're actually sending an analog waveform that corresponds to 0, 1, 0, 1, something. So this is the modulation here. And then somewhere here, that waveform is then put into this analog processing block. Here I put in all the RF up conversion, power amplifiers, all that good stuff. Antennas is kind of here. Then there's the propagation medium. There's all the analog processing here that then gives us the wave that we send over the air back to something that we can process in digital. This is demodulation. So this is like taking the waveform, creating bits, correcting errors, reducing the redundancy, essentially undoing each of these operations here. Now we're going to spend basically all of Wednesday talking about each of these pieces here. So I've only glossed over it, but we'll go through each of them in a little bit more detail. And so this is the typical blocks here. Where we're going to focus on in the class is primarily this and this, and we're going to develop a model for this to do that. So basically modulation, demodulation, modeling the channel, and that's where that's the emphasis here. So the motivation here is that, why DSP? Well, first of all, there's why signal processing and why digital signal processing. So you remember, if you're taking a signal processing class lately, you remember there's the system, there's the input and the output. We spent so much time in DSP characterizing the system as a function of the input and the output and the transfer function, and we compute its Fourier transform, and we do it in the Laplace domain, Z domain, and so on and so on. It's great stuff. So what we can do is we can think about communication systems in terms of inputs, outputs, and systems. We can write each of these blocks could be a system. So, you know, you could have a discrete time system, a continuous time system, a nonlinear system, a sampling device. You can have binary information, discrete time, continuous time, you know, and you could have different inputs and outputs depending on the kind of system that you have here. And so essentially what we're going to do is we're going to think about communication systems using the tools, the mathematical framework of signal processing. And this is not really a big departure from communications, but it was about 15 years ago, the communications and signal processing were quite different. And so in the last 15 years, they've come together a bit in this area that's called signal processing for communication. So it's really all about thinking about communication systems from a signal processing perspective. And then by doing that, you get new insights and you can figure out better algorithms and so on here. So that's like the motivation here. Now, let me tell you about the course here. So when we first started this class, we had an analog communication course at UT. We don't have that course anymore. Many of you have not taken it because it's not even been offered for 5 years. Now, in the class here, I'm not going to tell you that analog communication is not interesting here. But what I mean here is that we're not going to talk about AM or FM communication. Totally irrelevant. Not used in any of the wireless standards I told you about, except for 1G cellular, which was expired 15, 20 years ago. Everything is digital communication now. So we're going to focus on digital communication. We're not going to focus on analog. I don't mean that analog waveforms are not important. We will have analog waveforms all over the place, but we will be using the principles of digital communication to generate those analog waveforms. So that's premise one. Premise two is that wireless communication can be learned by all electrical engineers. I mean, if you have a good signal processing background, you should be able to learn wireless communication. You know what? Mechanical engineers, they also have signal processing background. They could learn it too, actually. I'm just thinking about that because this is the Building Brothers Mechanical Engineering. The other premise here, you don't need to know anything about communications to learn about wireless communications. It seems strange because you might think, well, I need to know wired communication before I learn wireless because, I'm taking away the wire. Not really true. The principles are the same, and when we approach it from a DSP perspective, we don't need that background. So we don't have to follow a traditional course sequence. And the final point here is that I also believe that you can implement it while you learn it. So you don't need to do all of this math, and then 5 years later when you get a job, implement it. You can do it at the same time, and then it connects the math to the real world here. So we're going to learn digital communication from a DSP perspective. We're not going to do everything in digital communication. That's too hard. There's a lot. That's a good class in its own right. We're going to do select topics in digital communication. We're going to incorporate modulation, channel estimation, equalization, synchronization. Many of these are not taught in other courses, especially synchronization. This is very important, almost always overlooked. We're going to use algorithmic design examples. So like for modulation, we'll talk about quadrature amplitude modulation and OFDM as a modulation technique. We won't talk about all the other 100 modulation techniques that you might talk about in digital communications. We're just going to talk about those two. They're actually used almost everywhere. It's fine. We're going to talk about a specific kind of channel estimation called least squares. We're not going to talk about maximum likelihood, map, estimation theory. We're going to talk about this one estimator. So the whole approach to the class is we're going to use specific algorithms to do things. Later on, if you take a graduate class or you go work in industry, you can develop other algorithms and better algorithms. That's no problem. So we're not going to. So I guess what I'm saying is we're not going to dive deep in one area. Instead, we're going to look at the whole system. And so we're going to take pieces from the whole system and put them together. We're going to use software-defined radio prototype to build everything. And this is going to be built using what's called the USRP and LabVIEW. So I'll tell you a little bit about that now. So just some of the technical concepts in the course. This is like an overview of the lecture outline, which is already on Blackboard. We're going to talk about sampling, up conversion, down conversion, channel modeling, power spectrum, QAM modulation, channel estimation, frame synchronization, equalization, standards, channel models, multiple antennas. Now the notes that I have covers this, and this. The standards I don't have in the notes. I just 2 lectures that I cover, and I've debated back and forth about creating notes, but it's really hard to summarize a standard in like even 40 pages. So I'm thinking I'm giving up on writing that up. And then the last one is multiple antennas. And I actually hope by the time we get there that I have written that chapter, and then I'll be done. I'm going to ship it over to the publisher, and hopefully they'll approve it, and I'll get it printed. Anyway, so that's like my goal this semester, is to write that chapter and give you a high-quality experience. So more or less, though, all this other stuff here, which is what we're going to do until about lecture 22, is all written nicely in the book there. That's available for free online. You know, here's a rough outline of the course. This is like way too much detail here, but you know, essentially mathematical preliminaries. Because you're coming from different backgrounds, we're going to talk a little bit about stochastic processes, I'm sorry to say. Those of you that have seen them probably don't like them. We're talking about that. We're talking about sampling theory. Transforms, we're going to use continuous Fourier transform, discrete Fourier transform, discrete time Fourier transform, maybe even Z transform. Yeah, transforms. And then we're talking about basics of digital communication. And so here we talk about kind of the ideal communication system. And then we talk about, well, reality, that's not how it works. And we add all these other impairments. So, and we're going to talk about algorithms to fix them. So that's the channel impairments area here. We're talking about equalization and synchronization. Then we wrap up with talk about standards and then fading channels. So what this is here, a typical wireless course that you would take actually starts here. It starts with, okay, there's this thing called the propagation medium. Here's how we model it, and here's what path loss is. We talk all about that at the end, because this is all interesting from a mathematical perspective. We can use it to do performance analysis, understand the effects of fading, but this is completely useless for us in the lab, because it's all about mathematical models. This is the stuff we need to implement everything in the lab. And so when we're done with the stuff that we need to implement everything in the lab, which is essentially here, then we start covering other topics related to wireless that are important, but we won't do it in the lab. So that's like the idea here. I think that's a really cool innovation. A lot of people, though, still just start off with the model, the channel, for whatever reason. And then we're going to wrap up with MIMO communication. I've actually squeezed in so much MIMO in this class. It's really impressive. I mean, I'm covering like 4 or 5 lectures of my advanced MIMO course here, all to you all here. So, and it's all explained using the same concepts that we talk about up here. And these are all the concepts that are in MIMO FDM, 802.11n, 4G. So it's essentially, you'll have a very good idea of the state of the art in wireless. And if we have time, you know, maybe we'll even talk about these massive MIMO and millimeter wave. I'll have to see. So that's the course content here. All right, that's a lot of stuff. And oh man, whoops, there's also a lab to go along with that fire hose of content. So the lab, first of all, it is physically in the ENS building, 113. It's the first floor. You walk in the door, you go all the way around back, and there's a set of double doors you've probably never been in because it's locked. That's the wireless lab, actually the Truchard wireless lab. This is the equipment that we're going to use. It's a USRP, Universal Software Radio Peripheral. I should have brought it. It's like about, I want to show you my laptop here, but it's smaller. The dimension is smaller than the sheet of paper, and then it's about that thick. And we have 2 of them. So this is used as a transmit. This is used as a receive antenna. And they're connected together with a cable. I know this seems kind of lame that we're transmitting and receiving. We have a cable in between. But before you do the more advanced stuff, we have to synchronize the 2 together, and it's just a very easy way to do it. So it's really just there for convenience, and we're not really like sending, you know, your data over the cable. It's going from one antenna to the other. And then the other thing is there's an Ethernet cable here. So we do have a couple laptops in there, but the ideal scenario is that you take your laptop and plug it into that. And so you're going to work in a group of 2. So hopefully one of you has a laptop that has a gigabit Ethernet connection that can be plugged in there. And then that way you do the pre-labs and LabVIEW on your laptop, and then you just go, you run it in the lab. So that's essentially the idea. So you're going to work in a team of 2, and then, you know, unfortunately the software only works with Windows. I apologize. I mean, I'm also using a Mac, but only works with Windows. LabVIEW does work in Linux and in the Mac, but there's a couple of drivers for this setup that are just not developed yet. So fortunately, you have to resort to that. So hopefully one of you in the lab pair is not, you know, an alternative operating system user and can use Windows. So keep that in mind when selecting a lab partner, their preference in operating system. Okay, so just some background. Where does the lab fit in? Well, essentially, can you shut that door real quick here? Thank you. So essentially, the lab equipment is going to perform digital to analog conversion, RF up conversion. It's going to send the waveform. It's going to receive it. And so we're going to do everything here on a laptop, primarily the demodulation, the modulation and the demodulation here. So the lab will implement the analog, the circuits, all of that stuff for us. And we will operate in software, sending the appropriate waveform, binary information to the hardware, which will convert it to analog, send it to the RF, then we'll ship it over here, convert it back. So that's basically where the lab fits in. As far as content, primarily about the first third of the, not the first third, not like transforms and stochastic processes, but essentially the digital communication up to this point is what we do in the lab. So we do the modulation, demodulation, synchronization, channel estimation, and with OFDM and single carrier in the lab. And I know it sounds like a lot, but all the algorithms are going to be boiled down to something that's very, that you can deal with and implement without too much effort. I have a lab manual that is actually published by National Instruments, and it's bundled with the hardware. Again, huge bonus. It is free. We will make the PDF available to you. And this is now used at universities around the world, maybe 10 right now, but it's gaining popularity here. So we're going to use lab manual. Lab experiments have background information. They have a pre-lab, an experiment, and a post-lab. Typically, the way it works is that you do your pre-lab ahead of time. Then you come in the lab, you run an experiment, and if your pre-lab worked, which you have to turn in ahead of time, the lab experiment will be very quick. So you won't spend 3 hours in the lab if everything's working. If you didn't get everything working, you will be stuck in the lab the whole time. So most of the time, people work ahead of time in the pre-lab, then they come in and they do laboratory experiments and the post-lab. All right, outline of that, you'll see that. Sample pages, you'll see that. So summary of the course structure here. I realize I got like 2 minutes left. There'll be lectures, lab sessions, assignments. There are a lot of things in the course. Now, I'm spending a fair amount of time trying not to overload you with any of these topics, but it's kind of an unfortunate fact that there's just a bunch of stuff to do, and it doesn't take long, but there's a bunch of it. So the homeworks will not be very long in the sense of not many problems, but we have to have some homework because there is a theory component, and then the labs, you'll do a pre-lab, you'll turn it in, you'll do a lab report, and after the completion here. So you can do it. Don't be intimidated by this. It is 4 credits as an undergraduate. Graduate students, it's only 3 credits. Sorry, you guys are supposed to work harder. What can I say? But you can do it, and if there's ever some concerns, let me know. I mean, if you feel like it's really beyond what you should be expecting, then let me know. Last year, I got feedback from basically all the undergraduate students that said that this was the longest, hardest course they ever took, and so I'm not that proud of that, sort of proud of it. But I am going to work a bit on the homework just to make it, because last year I thought, the homeworks have been too easy, so I added a few really tricky homeworks, and that turned out to be a big mistake. So I am going to put a lot of thought into making sure that the homeworks are a bit more reasonable. So if you heard bad things last year about the time, don't believe it. I mean, believe it, but it won't be true again. Okay, so the last couple of things I need to mention, I guess I'm now almost completely out of time. Graduate students, you have a final project. So you can do an implementation, a literature review, or a research paper. You'll have a project proposal on the final project. I'll talk about this later. I have the guidelines on the web here. But the thing I want to emphasize here is the grading is different. So what that means is that the grading is not the same, and that it's done differently. So at the end of the day, I take the graduate students' numbers and the undergraduate students' numbers and end up on separate spreadsheets. And I assign grades over here, and I assign grades over here. I don't assign them together. Okay, is that clear? Okay. someone is going to ask me this, like in lecture 20, if the graduate students and undergraduate students are graded the same way. And I hope that doesn't happen, man. Every year it happens. They're graded differently. You're graded differently. And that doesn't mean, though, that undergraduates, you all can be like, who cares, you know. We'll all be graded the same, so we'll all slack off and do poorly. So, you know, if you all do poorly together, then you're stuck. So, you know, do your best, and you can do that here. All right, so we're like basically out of time here. I'll skip some of the motivation, the differences with other classes. But preparation for next week, you should read chapters 1 and 2, which is posted online now. Next week, we're going to talk about digital communication. It's also going to be an overview of like a lot of the concepts. There's no lab this week. Don't go this week. Next week, we're going to have a tutorial on LabVIEW. And Lab 1 will be posted. And so I'm actually trying to figure out the tutorial. Because there's an event next week on Friday, we might cancel the Friday lab and have the tutorial Thursdays. So I'm trying to work that out right now. So those of you that are going to be participating in this event next Friday, watch out for that. And then the homework number 1, I should post by tomorrow, and that'll be due next week. All right. Yeah, I'm sorry for using up all the time here. So I'll be here for questions, and I'll be in my office hours between now and 11:45. So thank you.